Imagine buying a house sight unseen. You get the keys, you unlock the front door, and there's a guy just standing in your living room.
Which is, a pretty terrifying way to start a home renovation.
Right. Completely terrifying. And he looks at you and says, hey, just a heads up. The previous owner left a massive load-bearing oak table bolted to the center of the floor. Your new renovations have to connect to it perfectly, but you absolutely cannot move it, touch it, or scratch it.
Yeah, that sounds absurd in the real estate world, but it is the literal daily reality for engineers stepping into a new role.
Oh, 100%.
You join a team, you get access to the cloud environment, and you realize half the critical infrastructure was built manually in the web console by someone who left the company like 3 years ago.
It's just a totally undocumented mess. And, that nightmare scenario is exactly what we are tackling for you today in this deep dive. Whether you're prepping for the HashiCorp Terraform Associate exam or you're just trying to navigate an inherited AWS environment without burning the house down, we are breaking down the mechanics of Terraform data sources.
Exactly, because we really need to figure out how to write clean, modern Terraform code that interacts with that existing mess, but, safely.
Right, safely being the key word there. So where do we even start with this?
Well, to survive that kind of environment, we have to establish the core concept of the read-only window. That is the foundational boundary of what Terraform can and cannot touch. And honestly, it's the entire reason the data block exists as a completely separate entity from the resource block.
Okay, let's unpack that. Let's unpack the difference between those two blocks because anyone using Terraform is pretty much living and breathing resource blocks, right? You type resource, quote, Oz Binsums, end quote, and you just expect Terraform to spin up a database.
Yeah, because that resource block is a strict declaration of ownership.
All right.
You are telling Terraform State Engine, hey, you are now responsible for the life cycle of this object.
Right.
So if you change the code, Terraform will update the infrastructure. If you delete the block,
It destroys it.
exactly, Terraform will destroy the infrastructure. It is complete, unyielding control.
So going back to the house analogy, using a resource block is kind of like buying and assembling brand new furniture. Like you own it, you build it, you can take an axe to it and throw it out if you want.
Right.
But using a data block, using that specific data syntax in your configuration is like looking through a read-only window at that load-bearing oak table already sitting in the house.
That's a really good way to visualize it.
Yeah, like you can look through the glass, you can measure the dimensions, maybe note the exact shade of the wood so you can, match your new floorboards to it, but you cannot paint it. And you certainly cannot throw it out.
Yeah. And pulling those dimensions through the window is exactly what a data source does. You are fetching attributes like an IP address or a routing table ID into your working environment. And the reason the separation is so critical is purely about architectural safety.
How so?
Well, imagine you need the IP address of that manually created legacy database so your new web servers can talk to it. If you try to use a resource block to reference it...
Right, Terraform would think it owns it now.
Exactly. Terraform would assume it needs to take over management of that database. And because the existing database wouldn't perfectly match your new code...
Oh, no.
Yeah. Terraform might decide the best way to manage it is to destroy the old one and build a brand new one.
Which results in a catastrophic overwrite of production data, like a completely resume-generating event right there.
Totally. And the read-only window of a data source structurally prevents that. Terraform's engine processes a data block, and it knows, okay, my only job here is to perform an API query, read the result, and just hold that information in memory. It is a strictly enforced physical boundary in your code.
Man, that safety net makes a lot of sense. But practically speaking, when I look through this window into a massive enterprise AWS account, I am not just looking at one table in an empty room.
Right. It's rarely that simple.
I'm looking at a cluttered, massive warehouse with thousands of resources, instances, networks, you name it. How do we find the specific object we actually need through all that noise?
So that requires precision querying. And AWS provides really powerful data sources specifically designed to sift through that exact clutter. For anyone taking the exam or honestly just building real-world modules, there are 3 major ones that come up constantly.
All right, let's hear them.
Yeah, so they are OS Availability Zones, OS VPC, and OSAMI.
Okay, that first one, the OS availability zones data source, that is an absolute lifesaver because I've seen configurations where people just hard code us East 1A into their
Oh,
modules.
yeah, you see that all the time.
And the second they try to deploy to a region that doesn't even have a zone, or if that specific zone goes down for maintenance, their entire deployment just crashes.
Hard-coding infrastructure like that is just a trap. By using the data source, your code dynamically asks AWS, hey, give me a list of all healthy available zones in the region I am currently deploying to.
Right, which makes your modules completely region agnostic and incredibly resilient, too. You just tell it to reference the first item in the list it returns, and you're good to go.
Exactly. And then for virtual machines, we have the Asami data source.
The Amazon machine image.
Right, because cloud providers update these base images constantly to patch security vulnerabilities, right?
Mhm.
If you hard code an AMI ID,
Which is just a random string of numbers and letters anyway.
yeah, exactly. If you hard code it, your code is essentially deprecated the absolute moment AWS releases a patch. The Asami data source allows you to dynamically query AWS for the most recent official image that matches your specific operating system requirements.
Wait, hold on a minute. If I'm dynamically pulling the absolute latest AMI every single time I run my Terraform code, what stops an unannounced super buggy Amazon patch from just getting pulled in and breaking my entire production environment?
That is a very real danger. And it is exactly why data sources cannot be treated as just, blind grabs. You have to constrain the query.
Okay, how do we do that?
Inside your data source block, you use a filter block.
Hmm.
For the AMI, you don't just say, give me the newest Linux. You filter by the specific owner ID, which ensures it comes directly from Amazon, and you filter by the architecture, the root device type, and perhaps a specific naming convention that locks you into a stable release track.
Oh, I see. So the filter block is basically how we narrow our field of view through that window.
Precisely.
So how does that apply to the OS VPC data source? Because if I'm in an enterprise account with like 200 different network environments, I definitely do not want to accidentally grab the sandbox VPC and deploy a highly sensitive financial application into it.
Yeah, that would be bad.
Yeah.
For VPCs and really any organizational resource, the most robust way to filter is by using tags.
Oh, of course. Tags.
Right. Organizations rely heavily on tagging strategies to just make sense of their cloud sprawl.
Hmm.
So inside your OSVPC data source, you add a filter that essentially says, look through all 200 VPCs, but only return the one where the tag environment equals production and the tag department equals finance.
So you completely rely on the metadata, but wait, what happens if the query finds multiple VPCs that happen to share those exact same tags? Does it just like pick the first one it finds?
No, and this is a really crucial design philosophy of Terraform. It does not guess,
Ever.
ever. If a data source expects to return a single resource, but your filter is just a bit too broad, and it finds 3 matching VPCs, Terraform will throw an error and completely halt the execution.
Oh, wow, it just stops.
Yep, it demands a strict one-to-one mapping. The filter must be precise enough to narrow the view down to a single, unique object.
Okay, so applying strict tag filters handles our AWS resources beautifully, but my mind kind of goes to the boundaries of the cloud itself. What if the data I need is locked inside another team's Terraform configuration? Like, say the network team built the VPC, and I need the ID, but I don't want to query AWS directly for it because maybe I don't have the permissions.
You are hitting on a major architectural decision there. When teams separate their infrastructure into different Terraform workspaces, they create hard boundaries.
Right.
The network team outputs their VPC ID in their state file.
Hmm.
You, on the application team, need that ID. The traditional painful way to handle this is manual copy-pasting.
Ugh, the worst.
Right. Grabbing the ID from their console and pasting it as a hard-coded variable into your code.
Which completely defeats the entire purpose of automation, because the second they tear down and rebuild that VPC, my hard-coded ID is pointing to a ghost and my whole deployment fails.
Exactly. So the solution HashiCorp built for this is the Terraform Remote State data source. Instead of querying the cloud provider's API, this data source looks directly into another workspace's state file. It just reads the output's object of their state.
Oh, I love that. So rather than sneaking over to your neighbor's house with the tape measure to manually figure out the dimensions of their living room,
Right.
you just securely tap into their official architectural blueprints. If they update their living room, the blueprints update, and the next time I run my code, I automatically get the new dimensions.
That is the exact mechanism, yes. Terraform reaches into the S3 bucket or the Terraform Cloud workspace where that state file lives, downloads the JSON, and parses those outputs dynamically.
That's awesome.
It is, however, and this is a big however, This introduces a hidden architectural risk,
Oh, what's the risk?
tight coupling.
Ah, because I'm now entirely dependent on their state file being accessible to me.
Precisely. If your application deployment absolutely requires reading the networking team's state file, you have just tied the reliability of your code to the availability of their backend.
Right, so if their S3 bucket permissions change or their state file gets corrupted, or they just decide to rename one of their outputs.
Your deployment is suddenly hard-blocked. You've essentially expanded the blast radius of a failure across team boundaries.
Man, that makes total sense. It is incredibly powerful, but you have to monitor that dependency really closely.
You do.
Now, let's push the boundary even further. What if the data we need isn't in AWS, and it isn't in anyone's Terraform state file either?
Okay, where is it?
What if I need to query an internal proprietary company database to get some random configuration value before I can deploy?
Okay, so for systems that completely lack an official Terraform provider, HashiCorp gives us the external data source. This allows your Terraform run to execute a local script like Python, Ruby, or even just Bash directly on the machine that's running Terraform.
Okay.
The script reaches out to that internal database, performs its query, and feeds the result back to Terraform.
Wait a second. If Terraform has thousands of official providers covering almost every single technology on the planet, why on earth are we duct taping Python scripts into our infrastructure code? Doesn't that introduce a massive amount of fragility?
Oh, it introduces an incredible amount of fragility. The external data source is universally considered an absolute last resort.
Okay, good, because it sounds terrible.
It is. Think about a standard CI/CD pipeline. You write this clever Python script to hit that internal database, and it works flawlessly on your laptop.
Of course it does. It works on my machine.
Exactly. So you push your code, the pipeline runner picks it up, and it immediately crashes. Why? Because the pipeline runner doesn't have the requests library installed, or it's running an older version of Python.
Oh, man. You've introduced a hidden, unmanaged dependency just to run your deployment.
Furthermore, Terraform has a very strict requirement for how that external script must communicate. The script cannot just spit out a random text string. It absolutely must return data in valid JSON format.
Why JSON? I mean, why can't it just return a simple bash string if all I need is a single IP address?
Because of how Terraform builds its internal dependency graph, Terraform needs structured data to map to its internal dictionary structures.
Okay, that makes sense.
It needs keys and values so that downstream resources can predictably reference, data.external.myscript.result bracket, quote, IP address, quote, bracket. If the script's output deviates from strict JSON by even a single comma, Terraform fails.
Wow.
Yeah. It is a brilliant escape hatch when you truly have no other option, but it really should be avoided whenever possible.
Okay, message received. So we've looked at querying cloud APIs with filters, reading remote state files, and the absolute last resort of external JSON scripts. But I want to shift gears and talk about speed and mechanics.
Here.
If we have this massive enterprise setup with hundreds of these data sources open, pulling from AWS, pulling from S3 buckets, executing scripts, what happens to the speed of our deployment? Is Terraform really pinging Amazon for every single one of these?
Yes. Yes, it is.
Wait, really?
The underlying mechanic here is data source refresh behavior. During a deployment, Terraform goes through a plan phase and then an apply phase. Terraform makes the API calls to reread every single data source during the plan phase, and then it does again during the apply phase.
Both times. If I have a massive infrastructure, those network round trips would add minutes, maybe tens of minutes to the pipeline. Wouldn't it be way more efficient to just read it once during the plan and cache it?
It would definitely be faster,
Yeah.
but it would completely compromise Terraform's core guarantee, which is absolute state consistency.
How so?
Well, think about it. The plan phase might take 5 minutes to run. A human might review that plan for another 10 minutes before finally clicking approve. In that 15-minute window, the cloud environment could have changed.
Oh, I see.
Right, an IP address could have rotated.
Yeah.
If Terraform relied on cached data from 15 minutes ago, it might try to deploy a server into a subnet that literally no longer exists. Rereading at the apply phase ensures the infrastructure is built on real-time reality.
Okay, so the trade-off is speed for guaranteed accuracy. That makes perfect sense when you put it like that. But this constant refreshing mechanic makes me think about dependencies.
Okay, where are you going with this?
Let's say I'm writing a module. I have a resource block that creates a brand new database, and right below it, I have a data block that tries to query that exact same database to grab its connection string for a web server.
You are walking right into one of the most common pitfalls in Terraform and a classic scenario on the certification exam. You're using a data source to query a resource that has not been created yet.
Right. So during the plan phase, Terraform looks through the read-only window, sees the database isn't there yet, and probably just marks the data source result as known after apply, right? Like,
Yeah.
it knows it's going to build the database, so it just waits until the apply phase to look through the window again.
That is the logical assumption, and it is entirely wrong.
Wait, really?
Yes. If a data source references a resource that does not exist in the current real-world state, Terraform does not wait. It throws an error immediately at plan time and crashes the run.
It crashes at plan time. Why wouldn't it just map the dependency and wait? I mean, it knows it's going to create it.
Because data sources, by default, are evaluated during the initial graph construction. Terraform demands to know the state of the world before it promises you a clean plan.
Oh, wow.
If your web server's entire configuration depends on the attributes of a database, and Terraform cannot verify those attributes exist right now, it refuses to proceed. It's actually a protective mechanism.
So what are you supposed to do?
It forces you to either establish a strict explicit dependency using dependent, or, and this is the better way, re-architect your code so you aren't using a data source to fetch information you could just reference directly from the resource block itself.
Oh, that makes perfect sense. If you are creating the database in the same module, you already own it. Just reference ospinstance.mydb.endpoint. You don't need to look through a read-only window at furniture you are literally currently holding in your hands.
Precisely. You only use the window for things completely outside your immediate control.
Okay, let's put this to the test in the real world. Let's look at 3 headaches you might face tomorrow and see how these mechanics apply. Scenario 1. We are back in that messy, inherited AWS environment. You are tasked with deploying a new reporting application. It absolutely must live inside a legacy VPC managed by the finance team. It was built manually in the console years ago. You know it's there, but you don't know the ID, and you definitely don't want to accidentally delete it. How do you integrate it?
Okay. The requirements dictate the solution here.
Yeah.
Because we cannot risk altering it, resource blocks are completely off the table. We deploy an OSVPC data source.
Okay.
And to ensure we don't grab an unrelated legacy network, we implement a filter block, specifically querying the metadata tags, perhaps department equals finance and application equals legacy reporting. Terraform securely fetches the ID, holds it in memory, and safely passes it to our new application components.
Clean, safe, and precise. I like it. Okay, scenario 2.
Yeah.
You are writing a deployment for a massive application overhaul. You write a data source to fetch the Amazon resource. Name the ARN of a specialized security group. However, you just find out the security team is running way behind. They aren't going to build that security group until tomorrow morning. You push your code today just to see what the plan looks like. What happens?
Based on our earlier discussion, the timeline is the killer here.
Right, because I know Terraform rereads during the plan, so it queries AWS, looks for the security group, and comes up empty. Since it demands a one-to-one match and the resource literally doesn't exist yet, it's going to throw a plan time error today. It will not let me queue up a deployment for tomorrow.
Exactly. The run halts before a single resource can be modified. It reinforces the core value of predictable execution. You can't plan on a ghost.
Scenario 3, the final headache. Your front-end application needs the IP address of an internal load balancer. The networking team manages this load balancer, but they do it properly using Terraform. It's just in a completely separate workspace.
Okay.
You need that IP to feed into your DNS configuration. You could manually paste it. You could write a Python script to hit the AWS API, or you could use remote state.
Well, we can eliminate manual pasting immediately, right?
Yep.
It is static and incredibly fragile.
Yep, done.
And writing a Python script via the external data source introduces hidden dependencies on the CI/CD runner and requires that strict JSON formatting just to return a single string. It's too much overhead.
Which leaves the Terraform remote state data source. I can point my code at their state files output block and dynamically pull the IP. But I have to document that my deployment will now fail if their state backend goes down or if they revoke my read access. It's the best option, but it requires actual cross-team communication.
You perfectly map the technical execution to the architectural trade-offs there.
Yeah.
You are balancing automation against dependency management.
This has been incredibly clarifying. For everyone listening, let's just quickly lock in the core takeaways from all of this. The data block is your read-only window into existing infrastructure. Use it to measure the room without taking ownership of the furniture. When querying massive cloud environments, use the filter block, heavily relying on tags, to ensure you pull the exact resource and avoid those multiple result errors. We saw how Terraform Remote State lets you borrow blueprints from other teams, but definitely expands your failure blast radius.
Don't forget the duct tape.
Right. We learned why the external data source is a fragile, JSON-dependent last resort. And most importantly, we uncovered the planned time trap. Data sources execute immediately, guaranteeing your infrastructure is built on real-time accuracy, not assumptions.
Understanding those mechanics is just a profound shift in how you write infrastructure code. And, looking at how aggressive Terraform is about querying its environment leaves us with a really interesting philosophical question.
Oh, lay it on us.
If data sources force your deployment to constantly react to outside, manually created infrastructure at every single plan and apply, who is really dictating your system's state? Is it the declarative code you carefully wrote in your repository, or is it the unpredictable, messy environment your code is forced to live in?
Wow. That is a brilliant thought to chew on. I mean, you can buy the house and you can write the code to renovate it perfectly, but you are still just decorating around someone else's load-bearing furniture. Thanks for joining us for this deep dive. We'll catch you on the next one.